Employees prioritize operational speed over everything else. Generative AI offers such a productivity boost that users frequently bypass traditional corporate security guidelines. This creates a specific vulnerability documented as Sensitive Information Disclosure, or OWASP LLM02. Users seamlessly embed proprietary logic, financial data, and personal identifiers directly into conversational queries without realizing they are leaking data to external servers. The enterprise software industry typically addresses data leaks by routing traffic through cloud-based data loss prevention, or DLP services. These systems intercept the prompt and inspect it before it reaches the target AI model. But routing prompts through a cloud DLP creates a privacy paradox. To check if private data is leaking, the architecture requires sending that exact data to an external server. The data leaves your secure local perimeter before inspection even begins. Validating the safety of a prompt via a cloud service does not eliminate the risk of exposure. It simply moves the trust boundary from the LLM provider over to a separate third-party security vendor. If detecting an external data leak requires sending data externally, the only structurally secure solution is a zero-trust inspection pipeline hosted entirely on local hardware. Securing local traffic introduces a new problem: how to intercept it effectively. Developers often rely on SDK-integrated guardrails, injecting security logic directly into their application's source code. SDKs work for managed applications, but they leave end users exposed. They cannot monitor an employee pasting a proprietary contract directly into unmanaged third-party web interfaces like ChatGPT or Claude. To capture that web traffic, security teams deploy standalone browser extensions that read the document object model, intercepting text before the user clicks send. Browser extensions secure the web interface, but they are completely blind to programmatic traffic. They cannot monitor automated API calls, command line interfaces, or background IDE integrations like GitHub Copilot. Total coverage requires dual-layered interception, capturing both channels simultaneously. The architecture combines a browser extension for human-driven web traffic and a transparent proxy for programmatic HTTP streams. Furthermore, the proxy is specifically configured to capture persistent WebSocket secure traffic for modern inference APIs. Securing AI workflows requires absolute network interception across human interfaces and automated system channels, ensuring data is caught before it leaves the host machine. The Minos verdict mesh decouples network sensors from detection logic. Browser usage on the left warns or blocks the user directly within the web page. The API proxy on the right automatically drops illicit requests. Both streams converge into a unified local fast API server. Before reaching the core firewall, this backend acts as a sanitation checkpoint. It verifies MIME types, limits file sizes, and blocks path traversal attacks to ensure the engine only processes safe data. Decoupling network sensors from heavy detection logic gives organizations deployment flexibility. The entire stack can run locally on a developer's laptop, or the backend can scale up to a centralized enterprise server. Inside that backend lies the core engineering challenge: routing prompts through multiple complex models without introducing massive workflow-breaking latency. The initial theoretical approach involved a dynamic router LLM. An AI agent reads the incoming prompt and intelligently decides which specific detection nodes need to be activated. Empirical testing proved agentic routing fails in production. The inference overhead to ask an LLM what to do creates unacceptable latency. It also generates non-deterministic execution paths, meaning the exact same prompt could trigger different processing times. The production solution abandons the AI router for a strict directed acyclic graph, or DAG, state machine. The DAG utilizes conditional escalation. By applying strict branching rules, the system bypasses high-cost semantic models if low-cost deterministic engines hit an early block condition. Real-time security requires speed and predictability. Strict state-based branching preserves computational resources in a way dynamic AI decision-making cannot. The DAG routes data through 3 distinct analysis layers. Layer 1 uses deterministic pattern detectors. It runs strict regular expressions, keyword proximity windows, and checksum verification concurrently to instantly flag structured data, like social security or credit card numbers. Layer 2 introduces zero-shot named entity recognition, integrating models like Gliner. This layer identifies context-dependent entities, like specific organizational roles or project names, that lack predictable structural formats. The zero-shot capability is vital. It allows security architects to define and extract entirely novel entity categories on the fly, without needing labeled datasets or time-consuming model retraining. But layers 1 and 2 share a limitation. They cannot evaluate deep semantic intent. They fail when proprietary code is modified, or when sensitive information is deeply obfuscated inside conversational text. When early layers fail to resolve ambiguity, the graph escalates to layer 3, the LLM contextual reasoning agent. This serves as the final, computationally expensive backstop for semantic extraction. Triggering layer 3 introduces a critical vulnerability. Sending raw, unredacted prompts into an LLM detector exposes the exact sensitive payload the firewall is designed to protect. The architecture resolves this with a sanitization-first workflow. Before the prompt reaches the LLM agent, all deterministic and NER findings are scrubbed and replaced with typed placeholder tokens. By anonymizing the text first, the system allows the detection agent to perform contextual reasoning over the shape and structure of the data without ever having access to the sensitive values. To measure the operational viability of this local pipeline, the system was benchmarked against the Numatron PI dataset, tracking precision, recall, and total processing latency. This chart maps that performance. Down here in the bottom left is the minimal baseline configuration, relying almost entirely on deterministic rules. It executes in just 38 milliseconds, but yields a recall of only 47.3%. That means deterministic rules alone fail to identify over half the sensitive entities. Adding zero-shot NER changes the math. This new configuration moves sharply up the y-axis to 78% recall, shifting slightly right to 0.8 seconds of latency. This setup represents the optimal operational sweet spot. It achieves an 81.6% F1 score in under a second, a response time well within the acceptable limits for human-in-the-loop chat interfaces. Integrating a mid-tier semantic model bridges the intelligence gap left by traditional regex tools, and it does so without triggering the devastating latency tax of full LLM inference. To find the absolute upper limit of the framework's capability, the final benchmark bypassed the NER entirely and forced exhaustive LLM contextual analysis on every single prompt. Utilizing a locally hosted Gemma 3 model specifically fine-tuned for PII detection rockets the recall to 94.9%, but it drags the latency far to the right, hitting 5.4 seconds. That high F1 score proves a critical point. Small parameter, fine-tuned models running on local hardware can rival the detection capabilities of massive cloud-hosted frontier models. However, a 5.4-second delay per prompt is highly restrictive. It offers rigorous security, but it is likely too slow to support automated, high-frequency API workflows. The value of the DAG orchestrator is that it isn't a rigid, fixed product. It is a flexible mesh. Security teams can adjust the graph, sliding the precision latency scale to match their specific hardware limits and risk tolerance. By combining dual-layered network interception with a sanitized, conditionally routed backend, organizations can enforce strict data leakage prevention across their generative AI workflows, all while maintaining their absolute data sovereignty.